Hi, everyone. We had a great Zoom class today. Unfortunately, Zoom did not record the class. I'm going to blame Zoom. Could be me, I don't know. But anyway, I'm recording this after class. I will go over everything that we went through in the Zoom class. I'm kind of sad because it was a really good class. I had a couple people there. They were wonderful. Anyway, as you're watching this, you might want to go to our Canvas site and download something. So we're not going to get to this until later in the video, but there's something called an optional practice seat for Module 4 Zoom session. It will help you to when we're actually calculating variance and standard deviation. So you might want to pause this presentation, go grab that, and then come on back or not. All right, let's get started. So because this is it's just me and you watching. I'm going to go through this pretty quickly so that this isn't a terribly long video. I'm always here if you have questions. So here we go. One of the things that you want to walk away this week knowing for sure is something called the sum of squares. And it's short for the sum of squared deviations from the mean. We're going to do some practice with this, but it's a really important thing to have sort of under your belt after this week. So we have a couple different formulas that we can use to find the sum of squares. We have this formula called the definitional formula. It's my favorite. And so I know I went over this in the regular videos for the week, so I'm not going to belabor any points, but it's basically doing the following. We follow order of operations and do what's in parentheses first. We take each score, subtract the mean to get what we call a deviation score. And then we go to the next part, exponents. We square each of those deviation scores, and finally we add them all together. And that's the name, the sum of the squared deviations from the mean. There it is, the SS. We're also going to talk about a different kind of formula to find the exact same number, SS, sum of squares. It's called a computational formula. We use this when maybe our calculations are going to have some decimals. It just makes it a little bit easier. But it's a formula that doesn't really connect to what it actually is. It'll give you the right number, but I really do prefer the definitional formula. Okay, we're going to be learning about basically 4 main types of measures of variability. So as a quick reminder, last week we were talking about measures of central tendency, trying to find one number that sums up sort of the tendency of the distribution where scores tend to be centered, a measure of central tendency. So this week we're looking at another number, but instead of looking at where scores tend to cluster or the tendency for the center, we're looking at how scores vary in a distribution. So how are they different from each other? How do they spread out? This is variability. So the first thing we're going to be talking about is something called population variance. Population, as a reminder, means we know every member of the set. It's the total population. In research, we often don't know the whole population, but sometimes we are working with actual populations. And we can find out how much scores within a population vary from each other. This is called a measure of dispersion. If you think of dispersion as disperse, going away from. Like say I'm a mom and I have 5 kids and they're all over me and I say, disperse, go away from the center. That may be a bad example, but dispersion means how things are spread out from the center. That's a measure of dispersion. So population variance has a certain symbol and a formula. So the symbol for population variance is sigma, that's a lowercase sigma squared. It looks like a little O with a hat. Sigma squared is the symbol for population variance. And the formula for population variance is that sum of squares that we just talked about divided by n. Now, right now, you might already be saying, I can't keep it all in track. That's okay. We're going to take it one step at a time. So the next thing that we're going to be talking about in this presentation is population standard deviation. So we had variance. That's one way of describing how scores vary from the mean. But we also have something called population standard deviation. It's also a measure of dispersion, of how scores spread out from the mean. And this is the most commonly reported measure of variability. We're going to learn about variance in order to get to standard deviation, but we don't often use variance when we're describing data. So standard deviation is our gold standard. That's what we actually want. So how do we find standard deviation? We're going to just take the square root of the variance to get standard deviation. You'll notice that the symbol for standard deviation is just sigma, no longer has the squared. When we take the square root of something, we're eliminating that exponent. So this is our population standard deviation. We also have something called sample variance. We already talked about population variance, but sometimes we don't have access to the whole population. We only have a sample. And so this is another measure of dispersion. And this is the sample, or this is the formula, the symbol in the formula for sample variance. The symbol, instead of sigma squared for the population, is S squared. That means sample. So this is the variance in a sample. And you'll notice it's very similar to the formula for variance in a population, except for the denominator has n minus 1 in it. Now, my videos go through this in much greater detail. This doesn't really take the place of the videos for this week. So make sure that you are aware of why we have to adjust with n minus 1. I'll give you a little hint about it. The last thing we're going to be talking about is sample standard deviation. So we had population standard deviation, now we have sample standard deviation. Again, standard deviation, whether it be in a population or a sample, is the most commonly reported measure of variability. So here's the symbol and formula for sample standard deviation. We have the lowercase s. Now, sample variance was s squared. Sample deviation is just plain old s. We got rid of the exponent. How did we do that? We took the formula for sample variance and we took the square root of it. So we got rid of the exponent by taking the square root. All right, so these are the four major formulas that we're going to be talking about. So I'm going to give you a very quick recap from the video about why do we have different formulas for populations and samples. Well, there's a really good reason for this. A sample is supposed to represent a population. So if you look at these drawings down here, like for example on group A here, the lower drawing is the sample and it comes from this larger population, and B is the same and C is the same. And what you'll notice is that the samples have less variance than they do in the population. Populations are much larger and the spread of the scores are going to be larger. So when we are taking a sample, we're trying to say something about the population. But if we measure variance and standard deviation in a sample, it's going to underestimate what it really is in the population. And so what we do is we do that little adjustment, change in the denominator from n to n minus 1. When we make the denominator smaller, it makes your quotient bigger. It makes your answer bigger. And so when we divide by n minus 1, we're kind of adjusting for the fact that we have a sample and it's really underestimating what the variance or standard deviation would be in the population. So as a reminder, we pull samples because maybe we don't have access to the full population, but we really don't care about this sample. We care about what this sample says about some larger population. We're always looking to generalize, and we're going to be doing that with inferential statistics. Okay. So what we're going to do right now is we're going to try some practice problems. So I am going to, at this point, try to turn on my document camera. I'll pull it up, and you can see this now. I'm going to be offering some questions that are just like the ones that are in your homework and your quiz for this week. So here we go. Here's the first one. Oops. How can we describe the relationship between standard deviation and variance? To answer this question, we're going to work this out by just putting down what are the formulas for population variance is sigma squared. Population standard deviation is sigma. Sample variance is s squared. Sample standard deviation is just s. So what I can say is that variance, or no, I'm going to go backwards. I'm going to say that I'm going to say this, to find variance, you're going to square standard deviation. So if I want to know what, if let's say I know the standard deviation, I can square it to get the variance. If I know the standard deviation for a sample, I can square it to get the variance. And in reverse, if I know the variance, I can take the square root of it to get the sample. Same over here. If I know the variance in a population, I can take the square root of it to get the sample. So I'm going to just write this out as notes that you might want to write out too. So I'm going to say variance is standard deviation squared. So if I have a variance, let's say my variance is equal to 3. If I have a standard deviation of 3, my variance is 3 squared. It's going to be 9. So I know that variance is standard deviation squared. But I can also just reverse that and say standard deviation is the square root of the variance. So I'm going to abbreviate here. Standard deviation is the square root of variance. Okay, so this is the relationship. You can toggle back and forth. If you know one of these things, you can figure out the other if you know the relationship between them. So I'm going to just do this. Let's say we have a variance in a sample of 16. I can know what the standard deviation is because I know that standard deviation squared will give me the variance. What squared will give me 16? Or in other words, what is the square root of 16? And that's 4. So this is the relationship between these two things. All right, hopefully that makes some sense. All right, when we're talking about our sum of squared deviations, the word deviation is in there. We need to figure out what is a deviation. What is a deviation score? Our formula for deviation score, and this might be the first one you want to write down, is going to be, equals the score minus the mean. That will give you your deviation score. So I guess I'll write deviation here. The deviation score is equal to the score minus the mean. So in this case, the score is 18 and the mean is 30. So what is the deviation score? I know I've done this in the past. I've said 12. Well, it's negative 12, right? Negative 12. Because 18 minus 30 is negative 12. When I have a negative deviation score, that tells me that my score is below the mean. The mean is 30, and 18 is less than 30, so it's going to be on the left-hand side of the distribution. All right, that's a deviation score. Here's another deviation score. Again, I'm going to go ahead and write the formula, the score minus the mean. We don't go in the other direction. It's always the score minus the mean. We had a score of 18. We're going to subtract the mean of 15, and that gives us a deviation score of 3. We have to find those deviation scores on the way to figuring out our sum of squares, on the way to figuring out our variance and standard deviation, whether in a population or a sample. So this is a deviation score of 3. That tells me that the score of 18 is 3 units above the mean, basically, or 3 points above the mean. Okay, deviation score. All right. Now, you're going to be asked some questions like this, where you're given an n, maybe not, a mean of 15 and a standard deviation of 2. What is the population variance? Well, you're given 3 numbers here, but you only need to know one of them to figure out the variance. And this you can figure out when you know the relationship between variance and standard deviation. So we know that, we don't know the variance, but we know that the standard deviation is equal to 2. So sigma is equal to 2. So sigma squared must be equal to, what do you think? 4. So if I know the standard deviation, I can just square it to get the variance. If I know the variance, I can just take the square root to get the standard deviation. So these questions don't really require any calculations, really. Okay, similar question. Population of 40 scores, a mean of 75, standard deviation of 9. What is the variance of 9, excuse me. What is the population standard deviation? So let's put down what we know. The variance is 9. We don't know the standard deviation, but we know the relationship between variance and standard deviation. First of all, I'm also going to show you that you can have problems like this, but you can kind of cross out the things that you don't need. You don't need to know those things to answer this question. Sometimes they're there just to see if you really know this relationship between variance and standard deviation. So if sigma squared is 9, what must sigma be? You can do it a couple different ways. You can say, what squared will give me 9? Or you can say, what is the square root of 9 to get this standard deviation of 3? So these are easy. Once you know the relationship, you could do probably 100 of these in a minute. They're that easy. All right. Here's just a logic problem. The sample has 42 scores. How many of those 42 scores are used to calculate the range? So if you remember, the range formula is the high score minus the low score, and that'll give you the range. So let's just say we have the high score is 53 and the low score is 10. What is the range? Well, 53 minus 10 is 43. So the range just uses how many scores to figure it out. 1, 2. That's it. 2 scores. All right. But the range also doesn't really tell us very much. It gives us a rough idea of the low point, the high point, but we're going to use variance and standard deviation to tell us more about how the scores are distributed. And that uses every score in the distribution to figure it out. It's much better. All right. On an exam with a mean of 50, you have a score of 55. Would a larger or smaller standard deviation give you the higher position within the class? Okay, you're going to have questions like this, and what I'm going to recommend that you do is draw everything out. Now, I happen to have a handy-dandy drawn distribution here. I'm going to add some lines, though, because I like to have them. So let's go back and see what we had. We had the mean was 50, and the score was 55. And it's asking if this distribution has a standard deviation that's larger or smaller, which would give us a better standing in the group. So what I'm going to do is I'm going to try this out with 2 different standard deviations. I'm going to try it with a standard deviation of 2 and a standard deviation of 5. 2 is the smaller standard deviation, right? I mean, I'm being really specific here. 5 is the larger standard deviation. I'm going to map out what a score of 55 would be, if the mean is 50, in each of these 2 possible scenarios. So the first scenario I have is that my mean is 50. I'm going to put that here. And I'm going to start with the standard deviation of 2. So when you're solving a problem like this, you want to add 2 to each standard deviation to map out the scores in this distribution. So at one standard deviation, if one standard deviation is worth 2, 50 plus 2 is 52, and 52 plus 2 more is 54. 52 plus 2 more would be 56, right? On the other side, if I'm one standard deviation below, I'm 50 minus 2 to make 48, minus 2 to make 46, minus 2 to make 44. All right. So this is an example of what it would look like if the standard deviation was 2. And the score is going to be the same in both cases. My score is 55. But if I'm with a group of students that are in this distribution, my score of 55 would be right about there, right? So in this case, I'm doing better than everybody to the left of my score. That's a lot of people. That seems like a pretty high score. Let's try it with a standard deviation of 5 to see if that made any difference. So I'm still going to have my mean of 50. But this time, I'm going to add 5 to each standard deviation. So 50 plus 5 is 55. 55 plus 5 is 60, and 65. Then we go in the other direction. 50 minus 5 is 45, 40, and 35. Okay, so if I was in a class where the standard deviation of all the tests that were taken, for example, is 5, then the distribution would look something like this. Now we're going to locate our score of 55 on this distribution. It happens to be right here. There's 55. I'm going to draw the line up here. And now I'm doing better than this amount of people. So it's really clear to see that I did better when my standard deviation was smaller. Now, is that always going to be the case? It's not always going to be the case. What do I know about this score? I know it's above the mean. It's a good score. All right? So in the case where, and you might want to write this down, if my score is above the mean, I do better when the standard deviation is smaller. It makes my score more extreme. It makes me more extreme in the good direction, in the positive direction. But the question is it always the case? What happens if the score is lower than the mean? Does it still benefit me to have a smaller standard deviation? Let's take a look. We're going to actually, I think I can just use the same one. This time, we have the two scenarios, but this time, let's say that my score is, let's see, what did I have on the paper? I think it was 45. Okay, let me just double check. Excuse me. Yeah, 45. So let's see if we have a score of 45, if I do better if my standard deviation is 2 or 5. I still have the same scores if the standard deviation were 2, and the same scores if the standard deviation was 5. Let's locate 45 on the first one when the standard deviation is 2. Well, here's a score of 44, so my score of 45 in this case would be about there. That means that almost nobody is doing worse than me, and almost everybody is doing better than me in that case. When my standard deviation is 5, however, my score of 45 is here, and I'm doing better than if my standard deviation were 2. So if you think of it this way, smaller standard deviations push the scores out more. And that's good if you have a high score, but not so good if you have a low score. So if I have a score that's above the mean, I do better with a smaller standard deviation. If I have a score that's below the mean, I do better with a larger standard deviation. When in doubt, draw it out. That's what I say. Okay, here we're going to draw it again. Identify the values that represent about 68% of the scores in a symmetrical normal distribution with a mean of 20 and a standard deviation of 3. Okay, so we can so figure this out, but again, I really like drawing it out. I think it makes it easy. I want to remind you of a rule that we talked about in the videos, which is that 68% or so of the scores are between -1 and +1. 68% of the scores. That's a good chunk of them. This is something to just sort of memorize, that 68% of the scores in this normal distribution are between -1 and +1. Okay, so I can figure out at which two values are at -1 and +1 easily. First of all, I put my mean of 20 down here first. Good. Then I'm going to add a standard deviation to each point. 20 plus 3 is 23, plus 3 is 26, 29. And then I do the same backwards. I'm setting up my distribution, 17, 14, and 11, right? All right. Hope I did that math right. If not, you can correct me, but okay. So between what two values do 68% of the scores lie? 17 and 23. So your answer to this would be 17 and 23. That would be your answer. All right. So the next question is similar. I'm going to just say what that is. This says, identify the values that represent about 95% of the scores. Same mean, same standard deviation. Okay, 95%. So this is, again, something to just memorize, that 95% of the scores are in between -2 and +2. So I'm just going to draw a little thing and then say 95% here. Okay, 95% of the scores are between -2 and +2. So what are the values that separate 95% of the scores? Well, the low value we already determined was 14. The high value is 26. So your answer is 14 to 26 for a question like that. All right. Here we go. We are moving and shaking. Okay. Sometimes the statistics gods smile on you and they give you the sums of squares. You don't have to calculate them. You don't need to figure out the sum of square deviations and the mean. You're just given them. When that happens, you can just use the formula to figure out variance or standard deviation or whatever it is that you're asked about. But you need to figure out two things. First of all, figure out if it's variance or standard deviation that you're being asked about. In this case, it's variance. And then figure out if it's a sample or a population, and in this case, it's population. So what I'm going to do is I'm going to figure out, I said population. In this case, it's a sample. So my formula for a sample variance is going to be S squared equals the sums of squares divided by n minus 1, right? So again, this means sample variance, and the formula for that is your sums of squares divided by n minus 1. In a bit, we're going to be figuring out sums of squares, but you don't have to do that right now. It gives it to you, 36. So my answer for my variance is going to be 36 divided by my n of 5 minus 1. That makes 4. So 4 goes into 36 9 times. So in this case, your variance is 9. You can figure that out if you're given the sums of squares and the n. And spoiler alert, the standard deviation would be 3, right? Square root of the variance, but we're not going there. All right, this is it. This is where you're going to actually, if you want to, pull up that Excel sheet that I shared with you. We're going to find the variance and standard deviation for the following sample of scores. This is it. This is the big problem here. They won't get any more complex than this week. And it's not even that complex. So I'm going to minimize this. I'm going to pull up my Excel sheet that maybe you pulled up as well. And I'm going to just show you a couple different things about this sheet. First of all, I gave you a bunch of different sheets so that you can use this to practice with different ones if you want. It doesn't calculate it for you, but it gives you all the tools you need to calculate. Okay, so for sums of squares, we have two different formulas, the definitional formula and the computational formula. They're listed here, but then I rewrote the definitional formula here. So this is what we're going to do because we need to find the sums of squares to be able to figure out the standard deviation and the variance. Again, the directions said that it was a sample. So I'm going to go right to the symbol that has an S. So I remember sample S. Population is going to be the Greek symbols here. But this was a sample, so I'm going to use this formula here for variance and this one for standard deviation. Okay, so I'm going to first put the numbers here that were given to me, the 5 scores on the PowerPoint. I think that was it, right? 1, 3, 4, 5, 8. I think those were them. Okay, so this right here will lead you to figuring out your sums of squares. Remember, sums of squares stands for sum of squared deviations from the mean. So in the first step, you're going to take each score minus the mean. That's the deviation that we already did. We don't know the mean though, do we? So we need to figure that out. So what I'm going to do is add this up and divide it just to find the mean. 4, 8, 13, 21. It's 21 total divided by 5. And that means that our mean is 4.2, right? So what I'm going to do in the deviation column is I'm going to take each score 1 minus 4.2. And now I have a deviation score there. 3 minus 4.2. 4 minus 4.2. 5 minus 4.2. Oops, I need to put the equal sign first. And 8 minus 4.2. Okay. Now I have all of the deviation scores. Remember, sums of squared deviations is the sum of the squared deviations from the mean. We have the deviations from the mean. We need to square them next. Okay. Now, I know that my videos for this week go over this, but why are we squaring it? Why do we even do variance? It's all very confusing. The reason is we're looking for the average amount that scores vary from the mean. How do you find an average? You add up the total and divide it by the n. So we could do that. We could add up all these deviations and divide it by the n of 5. Let's do that. So I'm going to just sum these up first. I'm going to find the sum of all of these numbers and then divide it by 5. Uh-oh. I can't do that. When you have deviation scores, they do something terrible. They cancel each other out. You can't find an average deviation score. We have to square them, add them up, and unsquare it again later. So this is why we run into this problem. We want to know the average amount that scores are deviating from the mean, but we can't do that because of deviation scores. Nature, they cancel each other out. So what I'm going to have to do, according to our sums of square formula, is I have to square them. Sum of squared deviations. This is the squared deviation. So I'm going to take each deviation. I'm going to do this the quick way through Excel, and I'm going to square them. So I'm squaring each of these. So if you take a look, if you were to do negative 0.2 times negative 0.2, you'd end up with 0.04. That gets rid of all the negative signs. Now we can start to do some math with this. We couldn't do it before because we canceled everything out. So what do we have now? These are squared deviations, but SS is the sum of squared deviations. So now the last thing, we just need to sum all these up, add them up, in other words, sigma. So I'm going to add these all up. Okay, so now I know my sums of squares is going to be equal to 26.8, right? Okay. So once I know sums of squares, and by the way, once you know sums of squares, that is the hardest thing to figure out. It's not even that hard, but it's the thing to figure out. Once you have your sums of squares, you can just plug them into the formulas. That's all we're going to do. So for the first thing I'm looking at is my sample variance, and that is going to be equal to my sums of squares of 26.8 divided by my n minus 1. Well, my n is 5. There's 5 scores minus 1. And I hit return. And that gives me a variance of 6.7. Okay, you don't need to know this, but I'm going to just do a little Excel magic to check to make sure I did this variance correctly. And I do that by punching in the equal sign. I'm going to type in VAR, and you start to get a bunch of things. I'm looking for the variance of a sample, so I'm going to double click on var.s, And then it says, well, what do you want the variance of? So I go ahead and I select the 5 numbers here, and I put an end parenthesis, and I cross my fingers, and it's the same. Woo! So whatever I did it right. So you can always check your work, which is kind of cool with Excel. But okay, the last thing is the standard deviation. So we have variance, which is squared units. In other words, on average, these scores vary from the mean by 6.7 squared units. That doesn't make a lot of sense. So we want to get rid of the squaring. We want to get back to the original units. So we take this 6.7, we take the square root of it. See the formula here for standard deviation is just the square root of the variance. So we can do this. I'm doing it with Excel. You could do it with a calculator. Square root, and then I double click it, and then I punch in 6.7, and I hit return, and that gives me a standard deviation. Hold on, you know me, I've got to format these cells to be 2 digits because it'll drive me crazy otherwise. Okay, so our standard deviation in this case is 2.59. So you have all the tools here to figure this out. If you have questions as you're doing your homework, come back to this, rewind it, watch it again. You've got this. Okay. So I'm going to go back to my document camera for the next part. All right. So sometimes you're going to have questions that specifically ask you to use the computational formula. So we've been using the definitional formula. The last one we just did was the definitional formula for sums of squares. But we want to use the computational formula sometimes. It's interesting. We use the computational formula when we have numbers that are going to produce a lot of decimals. It just makes it easier. But for you as beginning in statistics, I recommend the definitional formula usually. All right, here we go. So I have to write the computational formula down first. This is in your readings, it's in your PowerPoint, it's in the videos, but it's basically the sum of the squared scores minus the sum of the scores squared divided by, and this is a population, divided by n. All right, so interesting, very interesting. Actually, all computationals are going to divide by n, not n minus 1. I take that back. So here we are. What are these? Order of operations for this says that you take each score, square it, and then add them up. You don't have to do that in this week. I will give that to you. So I give it to you here. The order of operations on this one says you add up all the scores first, and then you square that total. Again, you don't need to add up all the scores in questions like this. I gave it to you right here. So you can look and see, okay, what is that? Where is that? That is this one right here. And just sum of scores themselves are this one right here. All right. So this is just a matter of plugging in. We can plug in easily. So what is the sum of the squared scores? The sum of the squared scores, I just draw down, is 160. So I'm going to write that down, 160, right? Minus something in parentheses squared divided by, what's my n? I can put my n in already, 12. So what is the sum of the scores? It was given here, sum of the scores is 40. All right. So this, if I square 40, it's 1600 divided by 12. I'll get rid of this. All right. And I did this earlier, so I happen to know that 12 goes into 1600, 133.33 times. So I can easily just figure out what my sums of squares are going to be. It's going to be 160 minus 133.33. And what is that? I think it's 26.67. If I did that math wrong, it's close to that. You can do the math and figure it out, but I'm pretty sure that that's what it is. 26.67. So this would be your sums of squares. Okay, I know I'm ridiculously compulsive. I'm just going to do it because it goes on to the next question. So 160 minus 133.33. Did I do it right? I did. Okay, 26.67 is it. That is our sum of squares. Now, for the next problem, it's very similar. We still have 12 scores. We still have the same sum of the scores and the sum of the squared scores. This time it's saying, what is the value of the variance for this population? Okay, so we're looking for variance in a population. So variance, the symbol for variance in a population is sigma squared, and the formula is sums of squares divided by n. I have those formulas at the ready, I know. So I can easily figure this out. I know that my sums of squares was 26.67. My n was 12. Now I can't just do this in my head. So we have 26.67 divided by 12, and that gives us 2.22. So the variance for this population is 2.22. If we wanted to find the standard deviation, we would just take the square root of that. But it didn't ask for that, so we're not doing it. All right, we have one more. Just one. That's it. You can do this. And for this one, we're going back to our Excel sheet that has all of the things that we need. First of all, we want to know what it's asking us to do. This one's a two-part. It's asking us for variance and standard deviation, both of those things. Okay. And it's for a sample. All right. So I know that it's a sample, so it's going to be the variance formula is s squared equals the sums of squares divided by n minus 1 because it's a sample. And the standard deviation is just going to be the square root of that. Okay, I've got all this. I've got it all on the Excel sheet, so let's go there. There we go. Here's the Excel sheet. And I'm going to click on sheet 2 to get to another one. All right, because I'm still working on a sample. So this time my scores were 2, 6, 3, 2, and 4. Okay. Now, remember, I'm going to just go back up and look at those formulas here. I need the sums of squares divided by n minus 1 for the variance. I need the square root of that for the standard deviation, which means I need the sums of squares. My sums of squares, I take all the deviation scores, square them, and add them up. I can do that. So the first step, I got to find the mean because I don't know the mean. So I add up all these numbers, 8, 11, 15, is it 21? 4, 6? No, 17. What am I doing? 17? Yeah, 17 divided by 5. So my mean in this case is 3.4. So to find a deviation score for each one first, because I need to find the sum of the squared deviations, I need the deviations first, equals 2 minus 3.4, 6 minus 3.4, 3 minus 3.4, 2 minus 3.4. Whoops, did I need the equal sign for it to do math? And 4 minus 3.4. Now, I have the deviation scores. I'm going to do that thing that I told you about. I'm going to check to make sure that they add up to 0. Because if they do, I know I've done my deviation scores correctly because all deviation scores will add up to 0. So I'm just going to add them all up here. Phew, added up to 0. Now, if you are doing this and you have a bunch of decimals, sometimes it doesn't always add up to exactly 0 just because the decimals theoretically might go out to 5 or 6 or 7 or infinity number of places. So don't get too hung up on this. If it's close to 0, then you're probably in good shape. All right, here we go. The next step for the sum of squared deviations is to square the deviations. So I'm going to do that. I'm going to take each deviation and just do it quickly using Excel. You can check to make sure that I've done this right, but I'm just basically squaring each number, each deviation score. All right, last things last, it's the sum of the squared deviations. I have to add them up. So I'm going to click on sum, and I'm going to add it all up, and I have the sum of squared deviations of 11.2. It's good, but it doesn't tell me anything about variance and standard deviation yet. So I'm going to actually just copy these little labels here. All right. So here we go. I do know that my sums of squares is 11.2. Now I just plug in that sums of squares into the two formulas to figure out variance and standard deviation. So the first formula right here is 11.2 divided by n minus 1. Okay, I can do that. Equals 11.2 divided by my n of 5 minus 1. And notice I have to, if I'm doing it this way, I put them in parentheses so that the order of operations works well. So that gives me a variance of 2.8. I'm nervous. I'm going to check with Excel to see that I've done this right. So I'm going to do equals, and I want to find the variance of a sample. And it says, well, what are your numbers? I pick these numbers. Oh, thank goodness. I was not wrong. That scared me a little bit. And finally, for your last step, you have your variance. To find standard deviation, you're just taking the square root of that. So let's do that. I'm just doing it with Excel, but you could do it on your calculator. The square root of 2.8 is equal to 1.67 is your standard deviation. So what that means is that on average, the scores in this distribution, these 5 scores, vary from or differ from the mean by 1.67 units. That's the average distance that these scores are from the mean on average. Couldn't find the average here. We had to square it and then unsquare it back down after we found variance. Okay, I'm going to check this too because I just want to make sure. So I'm going to do standard deviation, stdev.s, standard deviation for a sample. And I'm going to pick my numbers and cross my fingers and all that good stuff. And it did. It actually goes out a couple more decimal places. Well, yeah, I guess I got rid of those before. Okay, this is it. So hopefully this is helpful to you. And as always, I'm here if you have questions. As you know, moving forward, we're not doing this whole thing in weeks to come. I will start to give you the standard deviation, and you're going to use that number in other calculations. But we do it now so that you really can figure out what it is, how standard deviation is found. Okay, I hope this was helpful.